Hi chemists, this is the last day of notes for our unit on nuclear chemistry. This is probably my favorite day of notes because we'll be focusing on some applications of nuclear chemistry. We'll be looking at fission, fusion, and applications. After this video, you should be able to describe what happens in a nuclear chain reaction, differentiate between fission and fusion reactions, and identify examples of how radioisotopes are used in everyday life. Recall that during transmutations, an atom can be converted into a different atom through radioactive decay or by bombarding a nucleus with particles. Today, we will focus on the latter by learning about fission and fusion. Let's first talk about nuclear fission. Fission occurs when a nucleus is split into smaller pieces. This process begins by colliding a nucleus with particles such as neutrons. The resulting nucleus is highly unstable and will decay. This causes something called a chain reaction, where the particles emitted from the initial reaction bombard other nuclei, causing them to also break apart. Here's an example. So a neutron collides with uranium-235. Uranium-236 is formed as a result, and then the uranium-236 atom is unstable and will decay, and this releases energy. The neutrons released from the decay of 236 will collide with other 235 atoms, repeating this process all over again, and that's why it's called a chain reaction. Let's talk a little bit about fission. So uranium-235 and plutonium-239 are the only fissionable isotopes. These reactions release a large amount of energy. Fusion occurs when the nuclei combine or fuse together to produce a new nucleus of greater mass. For example, production of energy from the sun. In the production of energy from the sun, notice that you take 4 hydrogen atoms, and they produce alpha particles, positron particles, and energy. This releases far more energy than any fission reactions. These reactions require extremely high temperatures in order to occur. Let's talk some more about some real-world applications, like C14 dating. Scientists often find the age of an object that was once living by measuring the amount of carbon-14 that it contains. Recall, C14 has a half-life of 5,730 years. This is its nuclear decay. All living things contain C12 and C14 in a fixed ratio. And so therefore, once an organism dies, the ratio of C14 to C12 changes, which allows archaeologists to estimate its age. The most accurate way to examine the C14 content is through use of a mass spectrometer. First, the carbon in the sample has to be converted into graphite or carbon dioxide. And then this can be done by burning the portion of the sample. The sample is then injected to a mass spectrometer and then ionized. Based on the path that the different isotopes take, we can determine how many C14 atoms are present in the sample. Here's an example of an image of a mass spectrometer. If you went on to study chemistry in upper level courses, you would undoubtedly work with one of these instruments in your classes. Let's talk about uranium-238. So what if all the C14 in the sample has decayed or the sample is non-living? Well, similar to carbon-14, uranium-238 is used to date specimens as well. Uranium is naturally found in most rocks, seawater, and in Earth's crust. It has a half-life of 4.5 billion years. And uranium-238 is specifically used in dating rocks and fossils. Iodine-131, very important radioisotope. This is used to diagnose medical problems or treat diseases. Specifically, iodine-131 is a radioisotope given to patients to check for an abnormal thyroid. Patients are given a drink containing the radioisotope, sodium, and then iodide, but the iodide is iodine-131. Since the thyroid extracts iodine ions from the bloodstream, the ions are absorbed and its radioactivity is used to create an image on a screen. From the image, doctors can examine the amount of iodine absorbed and determine if the person has hypothyroidism or thyroiditis. Let's talk about cobalt-60. The strong penetrating power of gamma rays allows it to be useful in the treatment of cancer. Cobalt-60, which is produced in particle accelerators, emit both beta and gamma radiation. Cobalt-60 is placed into a gun that is used to direct the radiation to where the tumor is located. The cells of the tumor are destroyed and it decreases in size. You have to be careful though, because gamma radiation can also destroy healthy cells, making those treated by this process very ill. Okay, chemists, I hope you found this interesting. It's amazing how much nuclear chemistry goes on in our lives. Thank you so much for watching.